This is Calculus 1, Lesson 21 on optimization, Section 4.7 in the book. And these are important applications of the derivative to often find the smallest or the largest value in a situation, or the minimum or maximum value of a function. So we talked about this a little bit in the last class. And today I'm just going to go through a number of the examples and some of the homework problems on optimization. So let us start with the following very nice problem. Suppose we have a parabola. So this is in section 4.7 of the book. Example 2. So we have the parabola y equals 4 minus x squared. So this is a parabola with the vertex at 4, opening down. This is 0 when x is plus or minus 2. So minus 2 plus 2, 4. The graph of the parabola looks something like that. And right here, this green point, so this point has coordinates 0, 4. This green point has coordinates 0, 2. And the problem is to find the point xy on the graph where the distance from xy to 0, 2 is minimized. So find xy on the parabola that minimizes the distance to the point 0, 2. So what you have to remember is the distance formula. If you have 2 points in the plane, x1, y1, and x2, y2, the distance between them, d, is given by the formula. D is the square root of the square of the difference of the x coordinates plus the square of the distance of the y coordinates. That's the distance formula. So here, if we take any point xy on the parabola, the distance from xy to 0, 2 is the square root of the difference of the x coordinates, x minus 0 squared, plus the difference of the y coordinates, y minus 2 squared. So this is the square root of x squared plus y minus 2 squared. But this is the parabola y equals 4 minus x squared. So y is 4 minus x squared. This is the square root of x squared plus, what is y? 4 minus x squared minus 2 all squared. And x squared plus 4 minus 2 is 2. 2 minus x squared all squared. Let's just expand this out. Square root of x squared plus 4 minus 4x squared plus x to the 4th, which is the square root of x to the 4th. 1 minus 4 is minus 3x squared plus 4. So this is the distance from a point xy on the parabola to the point 0, 2. We want to minimize that. Now, we can save a little bit of algebra, that is, get the right answer with a little bit less work, which is always a good thing to do, if we minimize the square of the distance. So suppose I let capital D be the distance squared, so you can get rid of the square root, that's x to the 4th minus 3x squared plus 4. And you want to minimize this. That means find the value of x for which this number is a relative minimum. So for that, we use calculus. So far, all we've used is high school algebra and geometry and some pre-calculus. So the distance d that we're interested in is x to the fourth minus 3x squared plus 4. So this is a function of x. So the derivative of this is 4x cubed minus 6x. Let's see. If I factor out a 4x, I get x squared minus 3/2. And that equals 0 when x is either 0 or plus or minus the square root of 3/2. Let's use the second derivative test. What's the second derivative of this function? It's 12x squared minus 6. So if you take the second derivative at 0, that's minus 6. It's negative. So x equals 0 is a relative maximum. We want minimum. What's the second derivative evaluated at plus or minus the square root of 3/2? That's 12. When you square this, you get 3/2 minus 6. That's 18 minus 6. That's 12, which is positive. So x equals plus or minus square root of 3/2. These are relative minimum. So when we're looking at this parabola, at these 2 points, x equals square root of 3 over 2 and minus the square root of 3, comma y. What's the y? Y for this parabola is 4 minus x squared. So that's 4 minus root 3/2 squared. 4 minus 3/2 is 5/2. So that's the answer. Those are the 2 points on the parabola closest to the point 0, 2. So that's a pretty example of a minimization problem. Let's do another problem. So in this problem, we have 2 posts standing in the ground 30 feet apart. So from here to here, that's 30 feet. And one of these posts is 28 feet high, and the other post is 12 feet high. And if you take any point x between 0 and 30, you can string a wire from x on the ground to the top of each post. And let's say the distance of this wire is y and the distance of this wire is z. And the problem is to find the point x on the ground that minimizes how much wire you have to use, which is y plus z. So for any point x, x determines y and z. Find x so that y plus z, the length of the 2 wires, is a minimum. So let's see. we can express y in terms of x, and we can express z in terms of x. Because what we have here is a right triangle. This is 12, this is x. So by the Pythagorean theorem, x squared plus 12 squared equals y squared. So y is the square root of x squared plus 144. And if we look at the right, this is another right triangle. This is 28. If this is x, this is 30 minus x. So z squared is 30 minus x squared plus 28 squared. Let's see, let's just expand this. This is 900 minus 60x plus x squared plus 28 squared. What is 28 squared? What is 28 squared? 8 eighths are 64. 8 twos are 16 plus 6 is 224. 56, 4, 8, 7. So z is the square root of this quantity. This is x squared minus 60x, and 900 plus 784 is 1684. So the total length of this wire, I'll call it L of x, it's a function of x, it's y plus z. But we just saw that y is the square root of x squared plus 144, and z is the square root of x squared minus 60x plus 1684. And we want to minimize that. So we have to differentiate and set the derivative equal to 0. So when you differentiate this is x squared plus 1/4 to the 144. You get 1/2, this to the minus 1/2, which is 1 over the square root of x squared plus 144, times 2 times x. And the 2's cancel. And when we differentiate this, we get 1/2, 1 over the square root of x squared minus 60x plus 1684. The derivative of this is 2x minus 60, or 2 times x minus 30. And again, the 2's cancel. And we want this to be equal to 0. We want to find the points where the derivative is 0. So that's the same as solving the equation x over square root of x squared plus 144. When we bring this to the other side, this is 30 minus x. Minus x minus 30 is 30 minus x over the square root of x squared minus 60x plus 1684. Which means, if I just cross multiply by the denominators, x times the square root of x squared minus 60x plus 1684 equals 30 minus x times the square root of x squared plus 144. So if I square both sides, I get x squared times x squared minus 60x plus 1684 equals 30 minus x squared, which is 900 minus 60x plus x squared, times x squared plus 144. Well, this is just maybe a kind of a mess, but we can still solve it. Let's just cross multiply. Let's just multiply through. This is x to the fourth minus 60x cubed plus 1684x squared equals, let's see, x squared times x squared is x to the fourth. I get 60x times x squared. That's minus 60x cubed. That's the x cubed term. What is the x squared term? I get 144x squared plus 900x squared. 144 plus 900 is, is that right? What's the coefficient of x squared? 900x squared plus 144x squared is 1044x squared. What's the coefficient of x? 60 times 144. That's minus 0. 6 4s are 24. 6 4s are 24. 26. 8 minus 8,640x plus 900 times 144. 9 times 144, you get 129600. So we get some kind of equation like that to solve, but fortunately, the x to the fourths cancel and the x cubes cancel. So this is really just a quadratic equation. So let me just write down again what that equation is. It's 640x squared plus 8,640x minus 129,600 equals 0. Turns out if you take out your calculator, the 320 divides all these numbers. So this becomes 2x squared plus, let's see, what is it? $8,640 divided by 320 is 27. And 129,600 divided by 320 is 405. And by a miracle, I believe this factors, because 405 is divisible by 9. So I believe this factors into x minus 9 times 2x plus 45. You get 2x squared. 45 minus 18 is 27. And 9 times 45. So x equal 9. And when is this equal to 0? X equal to minus 45 over 2. These are the critical numbers. And remember what the problem is. We have these two towers And we want to find an x between 0 and 30 that minimize the lengths of these two wires. So x has to be a number between 0 and 30. So x equal minus 45 over 2 is irrelevant to the problem, not the answer. So the only possibility is x equals 9. So if you place this point in the ground 9 feet from the left, and so 21 feet from the right, and you calculate y and z, you'll find that gives you the minimum length of wire. Okay, well, this takes a little bit of work, but sometimes you have to do some work. This is example 5. So you have 4 feet of wire. And you're going to cut the wire into 2 pieces. And from one piece, you'll make a square. And from the other piece, you'll make a circle. And you want to find the maximum area of the square plus the circle. So of course, you remember the formulas for the area of a square and a circle. If the side of the square is x, the area is x squared. If the radius of the circle is r, the area is pi r squared. So you want to maximize the sum of the area of the square plus the area of the circle, subject to the constraint. The constraint is you only have 4 feet of wire. So the perimeter of the square plus the circumference of the circle, they have to be 4 feet long. You're going to use all the wire, because if you don't use all the wire, that's silly. You can get a bigger area by making either x or r bigger. So you're going to use up the whole wire. You're going to cut it into 2 pieces and make a square and a circle whose total perimeters, the perimeter of the square, the circumference of the circle, add up to 4. So what is the perimeter of the square? 4x. And what's the radius of what's the circumference of the circle? 2 pi r. That has to equal 4. Now, if the square has a perimeter of 4x, the perimeter of the circle will be what? No, sorry, let's just do it like this. So this is the constraint we have to satisfy. So the total area is x squared plus pi r squared. But this relation tells us what r is in terms of x. This says that 2 pi r is 4 minus 4x, or 4 times 1 minus x. So if you divide by 2 pi, you get that r is equal to this. So x squared plus pi r squared is x squared plus 4 over 2 is 2. So x squared plus pi, what is r squared? Two times 1 minus x over pi, all squared. So here again, let me just repeat this to make it a little bit clearer. You have a square of side x, the area is x squared. You have a circle of radius r, the area is pi r squared. So the sum of the two areas is x squared plus pi r squared. But the total perimeter of the two geometrical figures is 4, because you have 4 feet of wire. So the perimeter is 4x, the circumference is 2 pi r, that adds up to 4. If you solve this for r, you get r is 2 times 1 minus x over pi. So I put that in here. So my area is x squared plus pi times 4 times 1 minus x squared over pi squared. So this pi cancels one of these pi's. And I get, what do I get? X squared plus, I square this out, 4 times 1 minus 2x plus x squared over pi. So let me write this as 1 over pi, multiply this by pi. So I have pi x squared plus 4x squared. So that's pi plus 4 times x squared minus 8x plus 4. That's my area as a function of x. So I want to differentiate this to find the critical points and see where this total area is maximized. So again, the area as a function of x is 1 over pi plus 4 times x squared minus 8x plus 4. A prime of x is 1 over pi, 2 times pi plus 4 times x minus 8. And we want that to be equal to 0. So 2 times pi plus 4 times x equals 8. So x, and 2 into 8 goes 4. So x is 4 over pi plus 4. Now, we're trying to, so let's go back to, remember the original problem. We have wire, 4 feet of it. We have a square of side x and a circle of radius r. This has perimeter 4x, and this has circumference 2 pi r, and the sum is 4. So in particular, for x less than or equal to 4, greater than or equal to 0, whatever x is, x is between 0 and 1. Now, when we're trying to find the absolute value of a function on a closed interval, we have to evaluate the function at the critical points and also at the endpoints of the interval. So here I have my different values of x, and here I'll put the area. So I have, first of all, the 0.4 over pi plus 4 in the inside of the interval, and the endpoints 0 and 1. So these are the endpoints of the interval. So when you let x equal 0, what I get is, when you get x equals 0, that's just the easiest thing to calculate. You get 4 over pi. When you let x equal 1, you get pi plus 4 minus 8 plus 4. So that's pi plus 4. Let me just put this in. You get 1 over pi plus 4 minus 8 plus 4. These numbers cancel. You get pi over pi, or 1. So at the endpoint at 1, you get 1. At the endpoint 0, you get 4 over pi. What about 4 over pi plus 4? So then you get 1 over pi plus 4 times 4 squared over pi plus 4 squared, minus 8 times 4 over pi plus 4, plus 4. So this is 16. This cancels one of those. This is pi plus 4. I get 16 minus 32 over pi plus 4 plus 4. So that's 1 over pi, 4 minus 16 over pi plus 4. And that's equal to 1 over pi times pi plus 4, 4 pi minus plus 16, 4 pi. I get 4 over pi plus 4. Aha, now, this is less than 1. This is 1, and this is bigger than 1. So what's the largest of all those numbers? X equals 0. So you maximize the total area by using all wire to make a circle. So the problem is, cut your wire up into 2 pieces, make a square out of one, make a circle out of the other, and do it in such a way that you maximize the total area. And the answer we've discovered is, don't make a square at all. Use 100% of the wire to make the circle, and that gives you the largest area. So that is actually a very interesting geometrical result. Let's do one more problem. So this is example 6. So this is a kind of a geometrical problem, and let me read it. The photographer is taking a picture of a 4-foot painting hung in an art gallery. So here's the wall of the art gallery, and here you have a painting which is 4 feet high. And a photographer is taking a picture of this painting, and his camera is placed at a position which is like directly straight ahead, 1 foot below the painting. So this is, the camera is going to be at this height. The only thing the photographer can change is the distance X from the camera to the wall. And so if this is the camera, here is the line of sight from the camera lens to the bottom of the painting. And this is the line of sight from the camera to the top of the painting. And this total angle here is some angle theta, but this angle is alpha, and this angle is beta. Oops, sorry. And this angle is beta. So the angle, the word is subtended. By the camera from the bottom to the top of the painting is beta, which in the notation that is being used is theta minus alpha. So let me draw another picture of this, so it's not in sort of three-dimensional perspective. The picture is the following. This is 0, this is 1, this is 4 feet higher, so it's 5. I have, for some point x, zero x, I have this angle beta. And this angle is alpha, and this whole angle is theta. So beta, that's the guy we're interested in, is theta minus alpha. And we want to choose x that makes beta as large as possible. So the object has to be to express beta somehow in terms of x. Now, let's see. If we look at this right triangle, we see that 1 over x is the tangent of alpha, or x over 1 is the cotangent of alpha. So x is the cotangent of alpha, right? Cotangent is adjacent side over opposite side. So we have this picture. Here's alpha. This is x, this is 1. The tangent is 1 over x. The cotangent is x, which means if I want to express alpha in terms of x, alpha is the arc cotangent of x. Now, beta is one I want to express, but it's easier to express beta in terms of alpha and theta. That's this very convenient formula. So what is theta? Well, I have another right triangle. Now this is 5, and this is x, and this is the angle theta. So x over 5 is the cotangent of theta, or x is 5 cotangent theta, or theta is the arc cotangent of x over 5. So we have that beta, which is theta minus alpha, is arc cotangent x over 5 minus the arc cotangent of x. Now, so beta is a function of x. Now we want to maximize beta. So we want to find d beta dx. So you have to know the derivative of the arc cotangent. So the derivative of the arc tangent is 1 over 1 plus x squared. And the derivative of the arc cotangent is the negative of that. It's minus 1 over 1 plus x squared. So the derivative of the arc cotangent of x over 5 is minus 1 over 1 plus x over 5 squared times the derivative of x over 5, which is a fifth, minus the derivative of the arc cotangent, which is minus, so minus times minus is plus, 1 over 1 plus x squared. So this is 1 over 1 plus x squared minus, let's see, this is x squared over 25. So I have minus 1 over 5 times 1 plus x squared over 25, which if you cross multiply gives you 1 over 1 plus x squared minus 5 over 25 plus x squared. So again, let me write this down. d beta dx is 1 over 1 plus x squared minus 5 over 25 plus x squared. And we want to set that equal to 0 because we want to maximize the function beta. So that's the same as saying 1 over 1 plus x squared equals 5 over 25 plus x squared. If you cross multiply, 25 plus x squared is 5 plus 5x squared. So 4x squared equals 20. X squared equals 5. X equals plus or minus the square root of 5. The distance has to be positive. So x is the square root of 5. And beta, the maximum angle you get, is the arc cotangent of square root of 5 over 5, 1 over the square root of 5, minus the arc cotangent of square root of 5. And one way or another, you can calculate that. Just use your calculator. Okay, so these are examples from the text of optimization problems. And in the next class, I'll go over some of the homework as well as the review for the second exam. And that is it for this lecture.